up here, and alright, so hopefully y'all can see my presentation pulled up here. So I just have a few slides put together. Shouldn't take real long, maybe 20 minutes to go through them, but I guess before that I can give a kind of a brief introduction to myself. I think I recognize most of you, but for those who I don't, I guess I can introduce myself. I'm Javan, Javan Miller, W8UA. I guess I've been licensed for a little bit over 3 years now. I'm really big into antennas, obviously. That's why I'm doing this presentation. Also into contesting and Morse code. So those are probably the three main things that I really enjoy doing in ham radios. So let's see. So let's kind of get started in this presentation here. Let me. All right. So let's see. All right, so thankfully I'm not going to be dealing with any of this math here. We don't have to worry about integrals or anything. What I'm talking about today is computerized antenna modeling. So thankfully other people who are smarter than myself have put these formulas and set up programs for us so we can model antennas to see how they perform. So basically what you do is you transfer an antenna system into numbers. For instance, you enter in antenna systems with wires and loads and other components. For instance, a 20-meter dipole would be a wire starting at XYZ coordinate 0, 0, 0 over to XYZ coordinate 0, 20, 0 for a halfway 40-meter dipole, and then feed point at the center of it. So just a way to enter the numbers into the program, and then the program processes those numbers and gives us some data back, like SWR, gain, and radiation patterns. And we'll get into all that later on here. So why would you want to model antennas? Well, first of all, you can optimize an existing antenna. For instance, you might wonder, what would happen if I would raise this up 5 feet? You think it would perform better? And how is it going to change other aspects? So you can change, optimize for something like that. And then also if you want to plan for a new antenna system, for instance, if I have, say, a dipole, a compromised antenna that's maybe only 40-meter antenna that's maybe only 5 meters off the ground and not an optimal height, if I want to compare that to a vertical or something for 40 meters, because verticals might inherently have a low elevation angle for the radiation, but a dipole might have more gain because of the ground reflection. So just you can plan for new antenna systems like that and just compare them, and also learn about any antenna. We'll get into this later on, but there's a number of models already made in this software of just pretty much every antenna out there. There's a model for included with this software. So you can learn just about every single antenna, and I think it's just amazing. And also you can have fun. I've spent countless hours just playing around with antennas, adjusting what happens if I do this or that, and I just think it's a lot of fun. So that's why you'd want to model antennas. Now there's a number of modeling software that you can choose from. You can see here, you may recognize a couple of them, like EasyNet here, and you can notice that EasyNet Pro 2 V6 was $525, but is now free, in fact. So we could be talking about that as well later on. And also Manigal, that's another free one. So today I'll just be talking about those two free options, since I always like free software. So anyways, so I'm going to be comparing both Manigal and EasyNet Pro 2, which are the two free ones. So there's a few reasons why I'd want to go with Manigal. I think it has a much better user interface. It looks a lot more recent, and I think it's a lot easier to understand, and especially if you're starting out. It has a few more features, like the 3D far field radiation plot. For instance, you can pan around a 3D representation of the radiation field, so I think that's a really cool feature. And then also there's an optimizing feature as well, and we'll be looking at this a little bit deeper later on. But basically what it does is you can tell it to optimize for a specific element, like SWR or gain or something, and it'll just a let's see, a portion of the antenna, whether it be the wire length or height above ground, to optimize the antenna for, say, SWR. So we'll also be looking at that because that is I think a really cool feature. And there's a few reasons why you may want to go with EasyNet. I believe it's better at modeling antennas close to the ground. I think Manigal has some issues with modeling antennas real close, like if you want to do an HF antenna a couple feet off the ground. I know some people put antennas like on their wooden fence, is like if they live in HOAs. So if you want to model something like that where the antenna is super close to the ground, maybe you'd want to go with EasyNet just so you get more accurate results. But other than that, Manigal and EasyNet and the rest are all very, very close in results. And also EasyNet you can design radial systems for the grounding, and so that's kind of an interesting point. So which one did I choose over here on the left? This is Manigal, with I think is much easier to understand, or EasyNet, which is I think a lot more complicated looking, and I think Manigal has a few more features that I like using. So I ended up going with Manigal, and so that's what I'm going to be looking at today. So I have a few slides here that go over some of the main aspects of this program, so we can kind of look into this and see how it works. So if any of you here on Zoom want to follow along and download this and set it up as we talk, feel free to do so. Here's the link over here, and of course a QR code as well. So let me get into this here and go through some of the tabs that are in the software. So right across the top here, there's 4 main tabs: geometry, view, calculate, and far field plots. Those are the 4 tabs that we're going to be going across, and I'll just kind of explain what's in each one of those tabs and how you can use that. So first off here, in this over here, this is just basically the name, and here is the frequency. This is the default frequency for the model, so this can be set to whatever you want. You can change it later on whenever you're calculating performance of an antenna, but it's a great way to just set it as a default kinda. And then in here, this is how you enter the wires, the antenna, as I mentioned earlier, and XYZ coordinates of the beginning of the wire and the end of the wire. So this line over here, this is for wire number 1, so you're just entering, this is the XYZ coordinates for the first side of the wire, and then X2, Y2, and Z2 are the XYZ coordinates of the other side of the wire. And this happens to be a 5-element 20-meter beam, but it just enter it in. Say it would just be a single dipole for 40 meters, a half-wave dipole. It would just be a single line here across, and you just do, say, 0, 0, 0 for X1, Y1, and Z1, and then X2 would be 0, and you could just do 20 for Y2, and then that would just mean a 20-meter long antenna in the wire in the Y-axis. And then over here are the sources for a feed point. Over here with POS, that's where you enter where the feed point is. So with W1C, that's wire number 1, so the first line up here, and then C is for center. You also can do W1B for wire 1 beginning, and W1E for wire 1 end, and whatever number you want. And then over here is the loads aspect over here. Same with the pulse, you just enter in W1C or whatever type. That's you just select from a drop down whether you want it to be an inductor, a capacitor, or resistor. So if you're making a loaded antenna, you don't want to add that over here with inductors in it to make the antenna electrically longer if you want to make it physically shorter. So that's how you'd add that in here. And let's see, I think that's pretty much it for this tab of it. Okay, so next up is the view tab. This is how you can excuse me, view the 3D model of the designed antennas. So you can pan around it and see if, did I position the feed point correctly, or the loads like the inductors, capacitors. Check to make sure you inserted those correctly. And then also, once you run the calculations on the antenna, it will show a current distribution along the wires. So it's kind of cool to see just where the distribution is, so you can see that. So Let's see. Next up, I'm going to look at the Calculate tab. Let me get a drink. And this is basically how you calculate everything, quite obviously. So up at the top is where you enter the frequency for the calculations. So I think it pulls the default frequency from the first page. This is just default, but you can definitely change it to for your calculation. And then you can select the ground, whether you want it to be in free space, perfect ground, or real ground. I generally use real just because we live in a real world, I guess. And with ground setup, you can enter in the characteristics of your ground system so you get a more realistic model what's going on there. And then with the height here, that's really important, especially if you're going to be doing like, I guess any antenna, but with a horizontal antenna, especially where the modeling is taking the ground reflections into effect with the gain and the pattern for the takeoff angle. That's really important to get an accurate representation of that. And then also over here you can change the wire type. There's 3 options, I think: copper, aluminum, and iron, I think. So just really important as well, just to make sure you have it takes the resistance and the velocity factor into effect to let you know how much gain you're losing in the wire with resistance and etc. So and then here at the bottom, this is how it spits out the data to you. Over here it gives you the complex impedance, so 52 minus 3 j ohms, and let's see. Oh yeah, sorry about that. So that's so I guess since it's -3, that means it's slightly the antenna's a little bit too short. So it's kind of a good way to be able to optimize antennas. Is if it's a negative number, it means you need to lengthen the antenna a little bit to make it higher or lower frequency resonance. If the number is positive, then you need to shorten the antenna a little bit. So that's just a quick way to be able to quickly optimize antennas as well. So then over here it has the SWR, and you also can change whether you want it to be for 50 ohms or 75 if your coax and transmitter are expecting 75 ohms. And then the gain with respect to dipole or dBi with respect to an isotropic radiator. I think it displays the gain over a dipole if you do it in free space, I think, and just dBi with a real ground. And then it also gives you the front to back ratio. The reason why that's so high in this case is because this is a 5-element 20-meter beam, so that's why the gain and the front to back ratio are so high. And then the elevation here, that is the takeoff angle at which it has the most gain out. So and that's pretty relevant, but we'll look in the next tab what gives you even a better representation of what happens. So let's see. On this here is an optimization feature, which I mentioned, and that's how you optimize for SWR gain or whatever. So that's on there as well. And then the plots, that allows you to plot SWR gain across a certain frequency range. So you can change here from the drop down the bandwidth. I just told it to give me a plot of the SWR in the 20-meter band, but I mean, you pretty much could tell it to scan the entire HF spectrum. It would just take a long time. It takes a little while to do all the calculations, but you can do whatever you want with this and see the SWR gain anywhere else. And last but not least is the far field plots tab, and you can see here is the azimuthal plot and the elevation plot, and you actually can click on the on this right here where the there's a cursor around here that you can drag around to, and up here it'll update the gain for that, so you can see what the gain is at different angles around the plot. And then also over here with the elevation as well, so you can see, oh, here at 10 degrees it's 9 dBi, down at 2 degrees it might be -5 dBi, and that's just really cool to be able to go around and see what it is at each angle. And and over here is the 3D far field plot, and it doesn't really look too good on a slide, but you can pan around it and get a 3D representation of the radiation plot. So I think that's pretty much all I got for the slides. Oh yeah, I had to put this in here. If you want to contact me, Javan at W8UA.com. And if you have any complaints, I'd set up this email, and I set up a role to go to my trash. So you can just send any complaints to complaints@W8UA.com. Let's see, that is all I got. So I was thinking I would kind of do a few demos, but before that, if anybody has any questions, feel free to ask them now. If not, then
I just loaded up the program and it came up with a vector plot. Is that the point you're going to start at?
So let's see. I think just start at let's see. Let me get this pulled up here. All right. So all right. So this is basically how you start modeling an antenna. Just entering the wires in here. Just with these coordinates. So that's basically what we're going to start with, Rick. All right, anything else before I continue? All right, so what I was thinking was I was just going to do a quick demo of modeling a 40-meter dipole just to get the basics down. Then I was thinking of modeling a trap dipole just to experiment with the loads and the optimization features to see how that works exactly. So so basically what we're going to do here is just add a wire. So a 40-meter dipole, we're just going to get 20 meters of wire horizontally and add the load in the center. And so that should be pretty straightforward. We can just enter in 20 here, and we can look over here at the view tab and see how that worked. And that was correct. So we can see over here that we have a 20-meter long wire, and that's that. So let's go back over here and add a feed point to this. So we're going to add that here at W1C. So that's wire 1 center. And then we can just leave that there because the voltage, we just leave at 1. And the phase degree, that only matters if you're doing a phase array of antennas. And we're not worrying about that. So that is pretty much it. View, you can see here that the feed point is in the center, that little red circle. Let's go over here to the Calculate tab to run some calculations on this. So let me change the frequency to 40 meters, and we have selected a real ground. Let me set the height here. We can just do 10 meters. That's about, what, 30 feet, so that's a pretty reasonable height. And we'll change the material here to copper wire. As I mentioned, there's copper, aluminum, and would that be iron, I guess. So choose copper here, and let me over here is the start button. That's what runs the calculations. So it was real quick there. You can see that actually happened to be just about the right length. But just so I can show how the optimization feature works on this, I am going to change the length of the antenna so we can let the optimization feature work for us. So I'm going to change this to 21 meters long. Then go back over here to the Calculate tab, and let's see here. All right, so then I'm going to pull up the optimization feature, and let's see what this does here is we can enter in what we want to optimize for and what aspect of the antenna that it can change to try to optimize it. So I am going to change the wire, and you can tell it what side of the wire to change. So I'm going to say on Y2, because remember the coordinates we entered for this was XYZ coordinate 1 was 0, 0, 0, and the second XYZ coordinate was 0, 20, 0. So I'm going to change Y2 for this. And you can change the step for how many calculations you want it to run to go ahead and optimize it for you. So we'll just leave that at 0.1. That's going to change the antenna length by 0.1 meter. Well, I guess we can put that down a little bit, and we'll change it to 0.05. Whoops. There we go. Okay, so 0.05. So it's going to adjust it to that. So let me hit the start feature here, and you can see right now it ran through the numbers there for a little while, and optimized it to a zero reactance, just a perfect resistive load. And you can see that SWR isn't actually 1-to-1, just because of the height above ground and other aspects. It's not exactly 50 ohms. So that's just a basic demo. Oh yeah, so let's go over here to the far field plots. So we now can see, you may be wondering why the azimuthal pattern here is not like a figure 8 like you're used to for a dipole antenna. Well, it's because this antenna is only a quarter wavelength above the ground, and so if we want to see that pattern, we can change the height here to 20 meters, which is a half wavelength high. Let me run the calculation again, and you can see here it actually changed the SWR to 2.3-to-1, so we can run the optimized feature again, and it got it down to 1.55-to-1 SWR, changed the length to 20.6 meters. And let's go back over here to the far fields plot tab, and you can see it's more of a figure 8, so that's even more of what you're expecting from the books. And I'm sure if we'd go up to a wavelength, it'd be even more defined, and more defined as you go up. More nulls here at the ends of the wire, and most gain at the with the broadside to the antenna. So as I mentioned, with this you can just put your cursor, if this works. Let's see. Oh yeah. So if you put your cursor on this, you can go around. If you watch this right here, the gain figures, you can go around and see, oh, at the ends it's 7.0 dBi gain, and or I guess broadsides to it, and at the ends you get -3 dBi of gain. So it's kind of cool just to be able to go around and see, if you put the antenna up and see, oh, what's it going to be at 50 degrees to Europe, or 140 degrees to South America, or whatever. You can just go around and see what that's going to be. And then also over here on the elevation side, as I mentioned, you can do the same thing over here, and just go around and see at what angle is what. And this is especially important if you're going to be using a software like HFTA, where it tells you the gain you have, or the predict, or let's see, there's a couple different programs. HFTA is one, and VOCAP's another. Tells you what elevation angle you need to make contact with a DX station. And so this is kind of a good way to be able to go around and see what gain your antenna is doing at each angle. And you can plug this into HFTA, which is high frequency terrain analysis program, and it actually analyzes your ground characteristics where you live, and so you can kind of use the two together to get a more accurate representation of how it's going to work for you. So and then next we have off this tab is the 3D far field plots tab, and it's not displaying correctly. All right, so this here is the 3D far field plots tab I was mentioning about, and you can just pan around and see what it looks like, which is pretty cool. So this is just a basic dipole up a half wavelength high above ground. So that's pretty much it for this one demo. I was thinking of doing a demo of a trap dipole just to see how a few more features of this works, but if any of you here would prefer something different, feel free to speak up here.
This is Kilo 8 Lima Fox. I was wondering, I've got a delta loop and I feed it in the corner, and I was curious, full wave for 40 meters.
All right. So, okay, yeah, I mean, we could model that here. That's a great idea. If you wanna do that, we can.
Yeah, that'd be cool.
All right. So let me just start over here. Jerome, do you have the like the dimensions of that antenna handy, or
Yeah, well, it's let me see, full wavelength at 40.
is it like
I
a perfect delta?
Yeah, well, one of
Okay,
it, I've got it both upside down and flat on the bottom, both of them feeding in the corner. So either way you want to do it, it's be cool.
I see. Okay, so it's a single point up at the top, and it comes down to horizontal at the bottom. Is that how
Right,
it
and
is?
fed in the
Okay,
corner. Yeah.
I see. Okay, so let's see. Let me just calculate here. That's be 40 divided by 3, so it'd be around 13.33 meters on each side. So let's see. So let me just do one wire across from 0 XYZ to 0 13.33 Y, and then that. So that's the horizontal piece, and then just Pythag here. Let me think. So that would be I need a real calculator here. If somebody has a calculator handy, let's see. So I need to let's see what would that be. That would be square root of so 13.33 squared. And let's see. Just doing some calculations here for what how high the top would be for that. So so that'd be that, and so that'd be 44.44, and then if I take the trying to remember this basic algebra here. So plus 44.44, and if I take the square root of that, hopefully that's right. So if I make the center, let's see, if I make the center, so 13.33 divided by 2, and then make that 14.91 high, and see if that looks right. And that's not quite right, I don't think. Yep. So I was wrong in my calculations. Yep, that didn't make sense. So let's see here. Let me, I guess, yeah, go ahead.
Your screen's not up, we just got you, if you want your screen up.
Oh. Sorry about that. Is that all right? There we go. Okay, so let me grab a real calculator so I can actually make this Pythag for the delta loop. All right. All right, sorry about that. I just had to get my trusty calculator so I could calculate what what that would be. So, so 13.33 divided by 2. Then we're gonna square that. Then we're also gonna square. Oh, I see what I did wrong. Square root of 13.33 squared minus 6.67 squared. So that would be, I see, that makes more sense now. So we're going to make the height be 11.54 meters high. And so we had this to the center here. So I did 13.33 divided by 2. So that's center of this. And then let me do the opposite here again. So I'm going to do that from 13.33 divided by 2, and then like that, and Let's see here. Sorry, just trying to think what's going on here. Okay, so nope, put this on the wrong side. So let me move that over to this side. All right, that should be better now. Yeah. All right, so let's see, who was that? Kate LF. Does that look about? I mean, is that what
Yeah,
you're thinking?
that's good. That's perfect. Yeah. Yeah.
Okay. So let me see here. So let me go back over here to the geometry tab and enter in a feed point. So we're going to do W1 E for the wire number 1. And so that's going to be the horizontal wire we did first. And let's just double check to make sure that's in the right spot. And that is correct. So let's see here. So let's go over here to the calculate tab. And by the way, this it's going to be a little bit more difficult if we want to try to optimize it, just because there's a lot of aspects, and I'm not sure if it's possible to. I know it's possible to optimize certain wires at once, but I don't think it can handle this correctly. So we're just going to try to kind of get in the ballpark and see what's going on. So I guess I'll make the base above ground maybe 3 meters high.
Yeah, that'd be good. Yeah.
Okay. And, oh, I see this is a little bit off, so let me just, instead of redrawing this, I'm just going to go up in frequency a little bit. I'm going to cheat. And let me go up a little bit higher. So we're at 7.5 megahertz, so that's way above the 40 meter band. Oh yeah, this is way too small.
I
of an antenna.
usually have a 2-to-1 balun in there, so it could be
Okay.
100 ohms.
Yep, well that makes sense. All right, so I'm watching here this is 120 minus 20J, so that would make sense that you would do a 2-to-1 balun, because we can see right here that it would be right here where it's resonant. I guess it'd be 7.85 megahertz where it'd be resonant. Yep. So if we look at this right here, it's 126 ohms, so half that would knock it down to 63 ohms. So that'd probably be a pretty good match. So I'm assuming that's kind of what you're seeing, Jerome.
Yeah, it resonates with a 2-to-1 balun. So
Nice.
I'd be interested in what it shows for the patterns, and then maybe at a multiple, like of what does it look like on 20 if it's
Yeah.
going to be 2 wavelengths.
Yeah. So this is the plot here on 40 meters. So let's see. I'm not exactly sure what side this is, so that's a really good reason why. Sorry, just something just went wrong there. All right, so sorry about that. All right, is this working? Yep. All right, sorry about that. So what I was saying with 3D far field plot, why this is really nice is because it puts the antenna drawing in this as well. So you can pan around this and see, oh, so the side opposite of the feed point has a big gnaw, and you can pan around, take the cursor around this here, and you can see opposite of that. Let's see, so this is at an elevation of 45 degrees, which is the peak. So you can see opposite of the feed point, it's negative 7.4 dBi of gain, which is really bad. But then on the broad side to the loop, you're getting a 2.5 dBi of gain at 45 degrees. So you can change this elevation to, say, 15 degrees, which would be good for working DX. So you can see the gain is around 0 dBi off the broadside to it, and negative 1.5 dBi off the side towards the side of the feed point, and negative 9.3 dBi off the opposite side. And then just here is the elevation plot for at 0 degrees. So, but yeah, that's pretty much it. Oh yeah, so you mentioned trying out other bands. So I guess I can just go to, let me go to higher, above 20 meters, because this is not an optimized antenna for 40. It would take me a couple minutes to figure that out, and don't want to do that right here. So let me just find the resonant point here around 20 meters, just so we get a more, a better, so we just get a better feeling for where we're at. So All right, so this is close enough. As you can see here, the feed point impedance has gone up, and so I'm not sure what SWR you're seeing on this, but it may be better to have even higher impedance transformer like a 4-to-1, but obviously it's not practical to switch it out, so you got to compromise somewhere and and pick a transformer that's going to work everywhere. So always a compromise, and you especially see that whenever you work with it here. So here's the radiation plot. It's wow, kind of interesting. I've never modeled a delta loop like this. So this is at elevation of 51 degrees. So it picked the elevation angle at which is the highest gain. So you can go around this here and watch the gain up there and see as it varies as you go around it. So yeah, interesting plot here up here on 20 meters. So yeah, very interesting antenna. I haven't done a whole lot of testing with these, so that's really cool.
Oh, okay, yeah, thanks. Yeah, that's pretty, gives me a little bit of, and I've downloaded the software. I haven't installed it yet, but I'm hoping to try that with that antenna.
Nice. Very good. So anybody else want to have an antenna they want modeled, or should I just try something else, or I guess...
Hey, Javen, you want to try a end fed with 49-to-1 unen with at 80 meters?
Yeah, sure. Let me do that. Rick, let me pull this up again. So, all right. So, so we're just gonna do a. Oh yeah, that's a really good point, Rick, because there's a few designs that actually have a compensating conductor. So I actually can go over that. I might want to pull up the specs here. I'm not sure. I guess I can pull up an existing model, but I guess we can kind of go over why some manufacturers put in one of those coils in there. So let me model this here. So Rick, are you thinking 80 meters for the end-fed half wave?
Yeah, that's, I think, what we could possibly get away with up at the UPD radio. We do end fed with chameleon balun. I think the chameleons are lower, something in the range of 6-to-1 or 9-to-1. I'm not sure.
Okay, so that'd be more of a random wire antenna. I see. All right, so let me just, we're just going to do an end-fed half wave here for 80 meters. So that would be around 40 meters long. So it's, let me just do this here. So again, this is 0, 0, 0 for the XYZ coordinates for the first point, and 0, 40, 0 for the second point. And then let me add a second wire as a counterpoint. So since this is an end-fed half-wave antenna, and the main half-wave of the antenna is on the one side of the feed point, we're just going to have a couple meter long, let's see, a counterpoise. Sorry, didn't know why it took me so long to think of that. And we also can kind of play around with some different counterpoise lengths to see what happens with that. But let me just add I don't know, maybe 3 meter wire on the opposite side. And that looks about right. So let me add a feed point to W1B. So that's wire number 1, the beginning of it. And all right, so I think that looks about right. So now if we want to change the feed point impedance that it's looking for, we can change it from 50 ohms up to the impedance that the 49-to-1 unen that you're going to be using in the end-fed half wave is going to be expecting on the other side. So if you multiply 50 times 49, that's about, I guess, 2450 ohms, I would think, right?
2450, that's correct.
All right, so if I go over here to, let's see, that would be set up over here. You can see right over here it changes. You can change what impedance or what resistance you want to be for the 1-to-1 SWR. So let me change that to 2450 here, and that looks about right. So let me go over here to 80 meters, which is the primary frequency we're going to be doing, and run a quick test. So this is, again, a real ground, 10 meters above the ground, and we'll choose copper wire for this. And you can see right here we have an SWR of 2.57 to 1, and you can see what the impedance is here, which is pretty interesting. It's It's much higher than the 49 to 1 the impedance that it's transforming the 50 ohms to. So um, now it's kind of makes sense why some manufacturers actually use 64 to 1, but we'll look on the other bands to see if we want to compromise what aspect or what impedance ratio we need for the transformer. So now we can go over to the other bands, and we're going to kind of see something interesting here. Is that let me see how to explain this. So the bands don't line up quite perfectly if you think about it. To make it an antenna that's going to be resonant, say on 14.200, about the middle of the band on 20 meters, or I guess 14.175 if you want to. That's in the exact middle. So it's going to have to be the resonant point on 40 meters is going to be half of that, so it's going to be around 7.08 or something megahertz is where the resonant point is going to be on 40 meters, and 480 it's going to be half of that. And just because of some ground affection or results and some different interactions and stuff, it actually might be a little bit lower than that. So you're not going to be able to make the antenna resonant up on high 80 meters. It's going to have to be resonant lower. And I guess so. Let me lower this a bit here, and so we can see what's going on. All right, so interesting. So I think what we're seeing here with the weird impedance is just because of the counterpoints we have selected. It's really weird how this works, and with an end-fed half wave, you want to have a good ground system or a good counterpoint system, be it a long coax run or something. So the impedance readings are going to be a little bit weird here with the counterpoise we have. So let me just change this to let's see what it works, how it works with a quarter wave on 20. Yeah, so it's still kind of being a little bit weird with us. But I guess we can go over here to the plots tab. This is another antenna that just kind of has some caveats to modeling it, which is kind of some weird stuff. But so I just pulled up the plots tab here so we can see a pattern of SWR here on 20 meters. So let me go over here to SWR as I mentioned earlier and change the bandwidth of the scan to 1 megahertz. So it's going to scan from 13.55 to 14.55 megahertz, and then it's doing a detailed scan here. So, and you can see that so you can see here that the resonance is much higher in the band. It's around 14.6 megahertz. So it's really crazy. We something that was resonant in the right point on 80 meters is now resonating way too high on 20 meters in the higher bands. So we're going to have to lengthen this a bit to even lower on 80 meters. So let me add another meter of length to 41 meters and see where the resonant point is on 80 now. So let's go back over here to the SWR tab and run another scan to see where the dip is on 80. All right, so you can see here that the dip is now much lower, around 3.4 megahertz on 80 meters. So we definitely are having a problem here. To have an antenna that's resonant on the higher bands, like 40 meters and 20 meters, we're actually going to have a inductor in the antenna. It's basically what it's going to do is adjust the resonance on the higher bands more than it's adjusting the resonance on the lower bands. So if you think of a 5 microhenry capacitor on 20 meters, it's going to have a much larger effect to the antenna than it would on 80 meters, just because on 20 meters an antenna is much smaller than it is on 80 resonant antennas. So I guess I can try to pull up a design here. I'm not sure if I have one handy, but I guess if not, I can just kind of guess, see what happens.
That's the coil that's like 7 or 8 feet from the end of the antenna with about 8 turns on it.
Yeah, yep. So that's what that's for. That's just to make the because that has more of an effect on the higher frequencies. As I mentioned, with the antennas are much smaller, and a certain inductance has much more effect on those frequencies. So I guess you said about 7-8 feet. I'm gonna do it, put it around 2.5 meters out. We'll just see what happens when we do that. So let me add another wire here, and then do one from 0, 0, 0 to 0, 2.50, and then do this from on the Y axis from 2.5 to 41. So let's just make sure it looks right here. Oh yeah, so when I added the second wire there, it kind of threw off my source or my feed point. So I'm gonna change that
Does
back
that
to
inductor go to the end? Is it towards the end of the coil, or is it closer to the beginning of the feed point?
So that's going to be the inductor is going to be close to the feed point.
Okay, yeah, I was thinking that was further out, but is that basically to act as a choke to cut the antenna equivalent length down at the higher frequencies?
So there is some designs with traps in these end-fed halfways, but that's not what this is doing here. This is not a trap. It's just an inductor that has more effect at the higher frequencies than it does at 80 meters. So that's what this is doing here. So over here I added a load. So this is wire number 2B for beginning, and then I can enter in, I don't know what, maybe 3 ohms, or sorry, 3 microhenries for the inductor. I'm not sure exactly what it'd be, but we can just try and see, and we can optimize later on. So and then right here is the Q. I guess we could do a Q of 200. Basically for those, a Q is basically the quality factor of the coil, and it's always better to have a higher Q. That means there's less loss in the coil. And also the one downside to having a inductor with a very high Q is it actually narrows the bandwidth of the antenna, but you prefer that over having a coil with a low Q, because that means you'll lose a lot of power into that. So let's go back over here to this view tab, and we can see that it properly placed the inductor right there. About I know it's kind of hard to see, it's real small in there, but that little X right there, it placed at around 2.5 meters away from the feed point. So let me run another scan here on 80 meters, and or actually let's go up to 20 meters again. And now that we know that it was previously resonant around, what was it, 14.6 megahertz, let me run another SWR scan and see where the resonance is at now. So let's go over here to plots and then SWR, and let me change the bandwidth out to further and run another detailed scan. And we can see here it dips right here in the 40 meter band around the low end, around the CW portion. So that looks just about right on 20 meters. Let's see what it looks like on 40 meters. So let's run another scan. So let's go to plots again, SWR. Let me change the bandwidth again to be further out. And it looks like it's resonant, a little bit low in the band, but that's I guess not too bad. So let's go up here to 15 meters and run another scan to see how this works. Let's go to plots again, SWR, change out the bandwidth to be wider there, and let's see here. And it looks like the resonance is too low, so that's good. Looks like the antenna is too long, which is what we wanted. Previously, we were battling issues with the antenna being resonant way too low on 80 meters, even outside of the band. And so it looks like this inductor brought down the resonance on the higher bands. And let's look to see what it did on 80 meters. My guess is it did very, very little to change that. So let's do another scan here of the SWR. And looks like the dip is around where it was before, so that's great. So again, that inductor just has more effect on the higher frequencies, and that's what we did to bring the resonance more closer to all the bands. So let me make the antenna a little bit shorter now. Now that we know the resonances were too low on the higher bands, actually all the bands now. So let me bring it down to 40.5 meters long. And run the scan again. And let's see what's going on here. Let me see what it's like on 80 meters. My guess is it's still, didn't make that large of an impact. Let's go on to 40 meters to see what happened with this change. Let me run another scan with this and see where it put the dip. So yeah, so shortening that helped a bit, but I think we can shorten this even a little bit more, which will help all the bands. All of them still have a little bit of a low resonance, so let me shorten the antenna even further to 40 meters long, and go back over here, and let me go back to 80 meters to see where the dip is here, and gotta bring it a little bit wider here. So yeah, so this is still set. The lowest SWR is at the bottom of the band. So we could improve this a little bit if we would increase the inductance. I'm not sure how much time you guys got and how long we should be working on this, but we could change the inductance here of this capacitor to say 5 microhenries, and that's going to have more of an impact of bringing down the resonance on the higher bands, and it's still not going to make a huge difference on 80 meters. So let me just shorten down the antenna here to just 39. Let's just go a little bit quicker here.
What quick question? What's the ratio? Is it 49 to 1 right now, or is it 64 to 1?
This is 49 to 1. So yeah, we can look at that a little bit later with the impedance and the ratio of the impedance. Yeah.
Yeah, if it tells you what the impedance is that it's resonant at, then we could adjust the number of turns to match that impedance.
Yep. Yeah, but as we're seeing right here on 80 meters, the impedance is around is much higher than 2450 ohms. So 64 to 1 would be better in this case, but we'll look at the higher bands and see what it looks like. So let's see here. So that looks like it brought up it brought the resonance higher in 80 meters. So let me run another scan. And yep, it brought it just to around the CWFT8 portion. So let me go over here to the higher bands and make sure we didn't mess anything up here, because we did two things at once. We both changed the inductor and the length. So let's see what impact that had on us over here. So let me change this just to a plot across all 40 meters and see. Also, the resonance is now higher in the 40 meter band, but it's pretty reasonable all across. So as you can see here, we can spend all day optimizing this antenna, and that's sometimes what I like to do, but don't want to bore all of you more than I already have. So so that's basically what we have here. We optimized it well enough. So let's now look at the transformer, the 49 to 1 transformer, and see if that's really the best option. So let me do another test here. So at 80 meters, we can see here that it's around 2,000 ohms. So that's 49 to 1's about perfect for that. Let's go over here to 40 meters, and we can see that this is about right. And you can see here that it's not exactly resonant. You can see here it's plus around 2000 J over here, so it's a little bit reactive. I think that's what it is, reactive, or I always confuse reactive and capacitive. I'm sure one of you guys knows far more about that than I do. You can correct me on that. And then let's go up here to 20 meters and see. And again, so you can just see it's going back and forth. So 49 to 1 and 64 to 1 should both work. It's just kind of more of a doesn't make a huge difference. But let me pull up a calculator here and just see what 64 would be. Okay, so it'd be around 3,200 ohms for that. And so you can see here it changed the SWR. I did not remember what that was before, so I'm just going to change it back and forth. So you can see here it's updating the SWR in real time for us. So let me go back. And all right, so yeah, they were both a few went up and a few went down, or one went down. So yeah, so it's just a compromise. I think if you change one, it's going to be better on one band, and if you change it to the other, it's going to be a little bit different on the other bands. So, but I think this is really a good example to see why that inductor here in the antenna is really important to bring all the bands into resonance. So, do you have anything else, Rick? Or?
Yeah, I guess that was a good question, because we saw in the article, which was I guess Utah Valley Amateur Radio Club is what Ted was just texted me where that article came from.
Oh, nice.
And they show the inductor, and the guy that was writing the article said, well, I used it once and I took it out and it didn't seem to make any difference. So this is a good way to show what it actually is doing, because I wasn't sure what the effect they were going after when they actually included that inductor. Puts a more of a plus J term into the equation. That brings it in a little bit. But we could do something even in between the two impedances, because it's easy enough thing to add another turn on the output to go from a 7-to-1 turns ratio to an 8-to-1 turns ratio, or higher or lower if you need to.
Yep, that's a good point. So I think just long story short, I think in conclusion, I think either would work well. Just kind of just what bands you want to focus on. So so that's pretty much this NFET half wave here. If anybody has anything else, don't want to keep you guys there at the library too long, but if anybody else has anything else, feel free to go.
Javan, I have a question.
Hey, how are you, Bill?
I'm doing okay. I usually run a tuner into a G5RV. So could a tuner be included in this set of machinations that you've been putting together?
So this program does not support tuners, but there is a couple programs out there. Let me pull up one that is included in the ARRL antenna book called TLW, Transmission Line for Windows. Let me see if I can pull that up here. I think I got that on here. So basically what you can do is enter in your antenna characteristics in the feed line, and it will calculate the tuner settings, the inductor and capacitor values, and you can enter in the Q of your tuner components, and it'll actually give you the losses in the tuner, which is kind of cool to see on certain bands. So Bill, is it just a feed line or window line directly to the tuner, or do you have some coax in there as well?
So I have a short length of coax between the transmitter and the tuner, and then I have coax out to the end of the ladder line of the G5RV, which is out there flapping in the breeze, and that at the end of the ladder line, of course, goes up to all the way up to the feed point.
I see. Okay, I guess there's a couple ways we could do it. I mean, we could even model the G5RV with the transmission line. If I let's see, if we think about it here, I could try to model the transmission line. It might take me a few minutes, and it might look a little bit boring, but I can do that real quickly here if you want. Just kind of.
We don't want to go too long for the folks who are in the library.
Yep.
Before they become overdue and have to pay fines.
Yep. Either way, whatever. I don't care whatever everybody wants to do. If I should look at this now, or if I should try something else, or whatever. Go ahead.
Javen,
Hey,
you see my message there? We can go till about 8:15 at the library, but if you need more time, you can always take host and we can wrap up here.
all right, thanks, Aaron. Yep, just don't want to do anything. Just don't want to bore you guys too much.
I think that would be a good application because we want to look at possibly modeling that chameleon 40 meter that we have at the roof of Auburn Science right now at some point down the road. But this would be a good test case for modeling a given antenna, which has a active vertical element to it.
All right, so I guess we can just go ahead and model a G5RV. If somebody wants to quick Google how much window lines in a G5RV, so I can model that. So I think, let me pull this up here. So I think the G5RV is 102 feet long. So let me pull up my trusty calculator and see converter here from length. So feet. So 51 meters long. So that'd be 15 0.55 meters on each side of the antenna, and then we're gonna have to model the window line as well. So I'm guessing the window line would be what, about an inch apart of the parallel wires.
That's about right. Maybe.
All right, so
I know. I'd say we were probably 2 inches is more.
2 inches.
Yeah.
All
It's
right.
about like that.
Okay. So if I put in 2 inches, that's about 0.05 meters. So if I change the y1 just to be 0.05 divided by 2, and then negative 0.25. So it's just going to be the wires from that to that, and then there's a 0.05 meter distance between the two, and then I'll just run two parallel wires for the feed line. So let's see. Did anybody find how long the feed line would be for the G5RV? What the default is?
I'm looking for it right now, but it's 300 ohm ladder line from the looks of the picture anyway.
Oh, so 300 ohm. Would that be closer then? So more like an inch? I guess it depends. What transmission line?
Yeah, ladder line, the impedance is based on the diameter of the conductors and the spacing to get the impedance.
Mm-hmm.
Not sure. Is there a way of putting in a feed line and giving it a certain impedance, or do you have to mod?
Yeah, so I don't think there's a way to add a feed line. There may be a way. I just haven't found it yet. So, oh, this might be it. Although I don't know exactly how this works. So, maybe I can look into this further and get back with you to see if that's how it works. But let's just run with this here with the feed line about 2 inches across and see how this works. So, what is it like? Does anybody know what the length of the ladder line is? If not, I can just look it up.
Hey, Javen,
Yeah, go ahead, Aaron.
what I'm looking up says open wire 34 feet, ladder line 30.6 feet.
Okay, so we can just do open wire for this since it's we made the spacing a little bit wider. So what was that, 34 feet you said, right?
Yeah.
Okay, so let me put this into my calculator here again. So that's 10.36 meters. So let me just for simplicity's sake here, I'm just gonna make the transmission line coming straight down from the antenna. So I'm gonna put the antenna up 11 meters high. So just changing the Z coordinates here. And then I'm going to bring down the wires from 11 meters high down to 11 minus the length of the wire, which would be 0.65 or whatever meters. So about 2 meters off the ground, or 2 feet off the ground. So let me do the, oh, I see I have an error here. Let's see, so I'm just adding the one wire of the one side, then I'll add the other wire of the transmission line. And then I'll do 11 minus 10.36, which was the 10.36 meters was the length of the feed line. And then we'll just do that on both sides. And then I'm going to be doing a bridging wire in between the two parallel wires for the parallel feed line, and then just do a load in the center of that. So there's really no good way to bridge a feed point across two parallel wires like that, except for doing a wire across the bottom. So that's what I'll do here. So let's see. Let me add in this here. As I said, sorry, it's just gonna take a little while to get this modeled. So, all right, so let me zoom in here just to make sure I got everything right. So it looks about right. You can see the two parallel wires and then the bridging wire across. Let me add the source to this. So it'll just be W5C, and then let's go back to the 3D representation and see, make sure the top looks good, and it looks right. So the one side's going to one leg and the other side of the line to the other. So I think this should be about right. There actually is a model of this already with the program for a G5RV, so I can pull that up as well and compare it to this to see what they modeled and how it's different. But we'll just go with what we drew up here and see what happens. So let me go to, say, 80 meters, and we're just going to keep it at the height it is. So right now it's around 35 feet high, and the feed line's coming straight down. So all right, so right here it's an SWR of 5.2 to 1 on 80 meters. So if I bring up that second app I have, let's see, this is TLW. If I pull this up, this window right here, let's see, what if, let me pull, if you give me a second, I'll make this a little bit more visible. Hang on here. All right, so let's see here. Sorry. All right, so this here is TLW. You can enter in the feed line. So Bill, how much coax do you have going from the antenna, the window line to your tuner?
Let's see. Let's call it 40 feet of RG58.
Okay. So we got a couple
I take
presets.
I take it back. It is RG8. Never mind.
Okay, so sorry, I forgot. You said 20 feet, was it?
40.
40. Okay. So there's a couple different ones here. I think it's built in 9913. So let's take it to 40 feet, as you said. And let's go take it to the frequency here to 3.55 megahertz, and enter in the impedance we got from Manigal. So that was 11.59 plus 22.15J in here, and right over here is the tuner. So you can put in the tuner you have. You can select the different options, whether it's an L tuner configuration or a T. Bill, do you know which one that is? If it's a which configuration? Oh, you're muted. You're still muted if you want to.
Pardon me.
No problem.
It's a MFJ 259, which I think is like an L tuner.
Okay, very good. So let me select that. I'm not sure if that'd be a high pass or low pass. I'm not sure which that is, but we'll just test one here and see what happens. So, so let's just select high pass L network here. The inductor Q would probably be around 200, and then we'll take the power to what, just 100 watts,
Yes.
And so, oh, so sorry. Gotta pull this up.
If you press one of these buttons and my radio starts smoking, I'm going to be mad at you.
Okay, let me, all right, we're just gonna have to, let me just pull up this other display here, and, you'll just have to look at it real closely. So sorry about that for you guys at the library. Not sure how big this is on your display, but, so here is a network here, and you can see, it gives you the voltage and current on each component of the tuner, and you can see actually this is pretty efficient. There is very little power lost in the tuner and very little power lost in the transmission line on 80 meters. So this looks pretty fine here. You can see there's only a total of 0.2 dB in the coax from the balance line to the tuner. So that's pretty good there on 40. Let me go back to Manigal and take it to 40 meters to see what the impedance is like, so we can enter that into the program. So let me pull this up again and see. Let's put in the change the frequency here to 7, so 40 meters, and then put in the impedance we grabbed from Manigal and plug this in here and do the tuner function again and run this again. Okay, so the tuner itself cannot match this solution. So you either can do this as a shunt. You need a shunt capacitor for the output, or I guess we could try the other L network configuration. That should be able to match it. So I'm not exactly sure how your tuner works. I'm not sure if it switches between the two, or Rick, maybe you know how the MFJ ones work, if it switches between the two, or if it has maybe a broader matching range. I don't know. But
Yeah, I don't know offhand. I have a couple downstairs. I'd have to tear them apart or take a look at schematics.
it sounds like a good project. All right, so yeah, so here on 40, it's not too bad. Again, at this frequency, we're not going to see a lot of coax loss for high or big SWR mismatch. So you can see a total of about 1 dB in loss, which is, again, pretty much nothing. And except for the capacitor here, is I see in the matching circuit, it's 637 picofarads. So again, this is just a test. I'm not sure what your tuner is like and what the components have in it, but that's what it'd be like in a hypothetical in this situation.
I would say the one nice thing about the tuner is it's got a little readout in the front, and then as you turn, you can tell it to tune up, and then it will tell you what values it's using for.
Oh wow, that's really cool.
The L and the C.
Nice. Yeah, I've never seen that before, so that's really cool. So let me just check here with Manigal and see what it looks like on 20. Let's see what the yep, so the SWR really isn't that bad. It's pretty much around 10 to 1 or lower. Let's see, on 20 it's around 7 to 1, which isn't that bad, I guess. Especially if you keep the coax between the balanced transmission line and your tuner pretty short. So yeah.
If
so,
that's like my MFJ, you can switch that capacitor from the antenna side to the radio side and back and forth. That was my
nice.
MFJ. So I think that might be similar to the tuner he has.
Very nice. Okay, so it can change the type of L matching circuit to be whether it's the impedance is one way or the other. That's cool. Nice.
I've never seen that feature. I'll have to check that out.
Interesting. Well, all I got here is just it's a T matching network, so I guess the most versatile. You don't have to switch it. You wouldn't have to switch it back and forth for the largest tuning range. But the only drawback is it's not as good of a performer, and it's lossier. So, but yeah, that's pretty much it for the G5 RV. So yeah, not too bad of a performer, just an average antenna.
And we had
Compromise.
one We had a G5 RV at the radio club years ago, and we didn't realize that it needed to have a decent tuner on it, and we never could get it to work very well. But the other problem was too, the feed line we didn't have it vertical. We had to have it horizontal because the distance between the roof and our towers weren't great enough to let the thing go straight down.
I see. Interesting.
Hey, Javen,
Yeah, go ahead.
we just got our warning at the library, so I don't know if you think you're at a good stopping point and want to
Yep.
take last minute questions, and we'll
Yeah.
start wrapping.
Yeah, go ahead, Aaron, and don't mind wrapping this up. If anybody else, I mean, I could stick on. Otherwise, I'd be glad to finish this up now. That's either way up to you, Aaron.
Well, if you got something to wrap up with this, go for it. I mean, it's up to you if you want to keep moving, but we'll start wrapping up here before too awful long.
All right, very good. So, all right, I guess I can call if anybody else has anything else they wanted to try. Otherwise, be glad to wrap up either way. Last call.
Okay. With the G5 RV, is there a way in the modeling to orient the feed line, the ladder line, horizontal instead of vertical? Or
Yes, for sure. Yep. Yep. So we definitely could rotate. We could just rotate this, to be honest. So, let me pull this up. All right. So hopefully you're seeing that now. All right. So I can just rotate this antenna in a particular. Let's see what coordinate would I want to rotate it, and I'm going to rotate it in X coordinate. So if I go to X over here and then do just 90 degrees just to make it flat. Oh, that was incorrect. So let me rotate with respect to Y now, 90, and now it's horizontal. So we can, I'll change this here to 5 meters above ground, or 10 meters above ground as we had before. And see here. So let me go back to. So this is kind of what you're thinking, Rick, just a horizontal feed line.
Yeah, because we don't have enough room to drop the feed line
Yeah.
directly down, and we basically
Yep.
just hang the feed line off from another tower.
Yep. Yeah, so this isn't making a big difference. It's as you'd expect. It's about the same. So I'm sure if you rotate the feed line closer to one of the elements, 45 degrees with that, it would definitely make a difference. But that'd be a little bit more difficult to model. But yeah, we could do that. That'd be kind of interesting to see. But horizontal should definitely be okay.
Okay, yeah, part of the problem was that it was kind of drooping on that account, but we don't have that much room between the top of the tower and top of the roof, and I'm not sure how good the roof is at being a ground plane. It is metal concrete with either rubber or overlay, and there's insulation between it, so that adds a little complexity, and I don't know if that would be worth trying to model or not. I think it'd be a trial and error at that point.
Yeah, I think modeling a sort of roof would it's definitely not within the capabilities of this program, and maybe it's feasible as something else, but I don't know. But as long as, I mean, if the feed line, the balance line is drooping, I think that's completely fine as long as it's more than a couple of the distance between the rule of thumb is keep at least the distance between the two parallel conductors, a couple of those away from any other metal object. So as long as you had it, I don't know, maybe 6 inches away from the roof, it should have been fine, I would think.
Okay, that might be part of the problem with the Carolina Windham. The vertical feed, it's actually a single coax that feeds it from another balun at the very end at the 50 ohm feed point. And that's up against a concrete building, so that's not too good. We didn't realize that was actually part of the radiating element when we put the thing up, or we would have we might still turn it around to see if it.
I see. So you have a 4-to-1 voltage balun at the top, and then a 1-to-1 current balun at the bottom of the vertical portion. Is that how it is?
I'm thinking so. I'm going to have to look at it kind of up to see what those
Yep.
baluns actually are.
Yep. All right, so I guess that's probably about it. Don't want to hold you guys up here, so I guess we'll pass it back to you guys there.